Okay, our next study on jumping biomechanics and jumping performance is a 2006 study by Ashby and Delp titled Optimal Control Simulations Reveal Mechanisms by Which Arm Movement Improves Standing Long Jump Performance. I switched up the order a little bit here. If you look on the schedule, it says number 7 here in jumping was going to be this study, Kip et al. On joint-specific and subject-specific strategies for kind of movement jump height. Since the previous study was about arm swing effects on vertical jumping, I thought I would change the order there a little bit, and after that one, do this one on arm swing effects on long jumping. So we'll still do the Kip study. We'll just do it after we wrap up this kind of mini section here on arm swing effects on jumping performance. This was another study that is a great example of the approach that I like to take, just kind of the theoretical or just general perspective that I like to take on sport biomechanics and biomechanics in general, where it's been observed that if you swing your arms, you can jump further than if you don't swing your arms. But that's not really biomechanics. That's just an observation of when I do this, this or that happens. When it becomes biomechanics, or at least when it becomes interesting biomechanics to me, is when we dig into the reasons why. When we say, okay, mechanically, what's going on there? Why does swinging my arms help me to jump a little bit further? That's where things start to be more interesting, and where we can gain some more confidence in whether this is something that we can use to improve performance consistently, or if it's going to be something that may just only work some of the time. Okay, this was another computer simulation study, and you'll see that we've done quite a few computer simulation studies recently, especially in this jumping section in class. This class is definitely biased towards my personal interests and expertise, and I do computer simulations. I like computer simulations, so that's one of the reasons we're covering studies like this. Also, there's just a lot of really good computer simulation studies in jumping biomechanics in particular. Not that there's not good simulation studies on other movements. There's plenty of great simulation studies, and I would say essentially every movement in biomechanics, but quite a bit in particular on jumping and jumping performance. So this is another one of those simulation studies. This paper is pretty technically dense in terms of details on the computer model and how the simulations were generated. And I'm guessing a lot of you are going to read the methods here and be like, what on earth is happening? Why is he making me read this stuff? Don't worry too much on the technical details of how they created this model and what it included and how the simulations were performed. It's conceptually similar to the couple previous studies we read on simulations of vertical jumping, where they had a computer model defined here, a model of the body in the sagittal plane, and it had a trunk segment, a thigh segment, shank segment, a foot segment, and then an arm segment here. And they applied torques here to the joints of the model, a torque at the shoulder, torque at the hip, torque at the knee, torque at the ankle, that then rotated the joints and pressed the feet into the ground and caused the model to move. Okay? The amount of torque that was generated at any particular joint at any particular time was, like the models of muscle that we talked about in the vertical jumping simulations, was a function of a hypothetical excitation signal coming from the model's nervous system sent to those joints that caused them to produce torque. And the amount of torque that was produced for a given excitation signal also depended on the angle of the joint, representing the muscle force-length relationship, and also on the velocity of the joint, how quickly it was flexing or extending and in what direction. So also including effects similar to the muscle force-velocity relationship. So this particular model didn't have like muscles per se, like the previous jumping models had, but the amount of torque that it could generate at any particular joint at any particular time was influenced by physiologically inspired constraints based on what factors we know affect how much force muscle can produce in terms of their length and velocity and activation level. So the model didn't strictly have muscles, but it did have factors that made it kind of behave like it did have muscles. Okay. So they then optimized, like in the previous studies, where they optimized the control signals or the excitations sent to the muscles to get the model to jump as high as possible. Here they did a similar thing, optimized the control signals sent to the joints to get it to use the joints and produce torques that made the model jump as far as possible. Okay. Here they were interested in the effects of arm swing, and so they were performing one simulation of jumping as far as possible with free arm swing, so while being allowed to generate a torque here at the shoulder that freely rotated the arm. And then another situation with restricted arm swing, where there was no torque here at the shoulder, and the shoulder was just simply locked at the side of the model, and it couldn't swing its arm and couldn't move its arms. Okay. Now, you might wonder, why do a computer simulation approach for a study like this? Why not just have people, actual human subjects, jump as far as they can with and without arm swing, and measure the biomechanics, and from there kind of see if you can tease out why they jumped further with the arms. There's generally two reasons why you might want to do a computer simulation study in biomechanics, or might want to have a computer simulation component to a study in biomechanics. Typically, we will do computer simulation studies either when we want to measure something that we can't measure on human subjects, like some outcome variable that we can't measure on human subjects, or where we want to perform a condition that can't be performed by live human subjects. Examples of the first reason here would be in some of the previous jumping studies that had actual models of muscle, where they wanted to know things like forces in individual muscles, or the amount of energy stored and returned by tendons, and things of that nature. Not measurements that we can easily take, at least not commonly and on a wide scale and non-invasively in human subjects. You can measure those things, but you're typically restricted to measuring them on like one muscle at a time or one tendon at a time, and they typically involve invasive measurements like, sticking some sort of fiber optic cable through the tendon, or surgically implanting a strain gauge on a tendon, and those are not things that are easy to get people to volunteer for, or easy to get ethics approval to do studies like that. It's really useful, cool data when you can get that kind of data, but it's not something that we can do in practice on wide scales or frequently. So generally we'll be using computer models to make measurements of variables like that from a model when we can't get them from easily from human subjects. I would say that wasn't really what they were doing here in this study, because this model here didn't actually have any muscles. It had joint torques that generated torques that were constrained to be influenced by physiological aspects of things kind of like muscles, but it didn't specifically have muscles, and they weren't particularly interested here in like what are the mechanics of like the hip extensors, and what are the mechanics of the individual plantar flexors. That wasn't really part of the research question here. So the use of the model here in this study was more along the lines of this second motivating reason for doing computer simulations, where you might want to perform a condition that can't be performed by human subjects, either for safety reasons or ethical reasons, or just simply humans can't do it, or can't do it reliably, or can't do it at all for whatever reason. Now that might seem kind of strange here, right? Like this was a study where the model jumped as far as it could without swinging its arms, and then jumped as far as it could while swinging its arms. You could get human subjects to do that. Like, what's the big deal? Here, I think it's largely a safety thing, and largely an influence of how that constraint, how jumping with the restricted arms would affect both the safety of the human subjects, and also their ability to truly jump as far as they could under those circumstances. Like if I have you guys all get up and go jump as far as you can and don't give you any other special instructions, you'll probably swing your arms, right? Unless I tell you don't swing your arms, if I just say jump as far as you can, you're probably going to swing your arms. If I then restrict you from swinging your arms, it may be hard to get you to not actually swing them at all, right? So it may be difficult to completely remove the influence of the arms. You might like kind of dampen them out and minimize your arm swing, but it might be difficult to literally not swing your arms at all. In a computer model, it's relatively easy to get the model to literally have no arm swing whatsoever and no influence of arm swing whatsoever on the movement. Also, if I have you not swing your arms when you jump, you probably haven't done that much or at all. It's probably not a very familiar motion, so you may not truly jump as far as you can. And because it's unfamiliar, you may feel uncomfortable doing it. You may feel unsafe doing it. You may land funny and awkwardly and hurt yourself. And so there's some safety reasons here. There's some safety factors to consider here. And also just the simple fact that my goal is to get people to jump as far as they can. And maybe they're just not truly jumping as far as they can because they don't feel safe, or they're just not very good at performing this motion. With the computer model, it doesn't really care about safety. It doesn't feel any pain, and if it happens to fall over, it's not a big deal. The model doesn't get hurt and injured, and you can just have it get up and try again. And so you can have greater confidence that the model is truly jumping as far as it could with and without arm swing. There's no confounding effects of safety or familiarity there. So that's the big advantage here, I think, of using a computer simulation approach for something like this. Okay, what result did they find? This is a great example of a study, again, that has a really nice abstract that concisely summarizes the findings here. So don't just read the abstract. I don't want to encourage you guys just to read the abstract. You should always read the full paper, but this is another example of a study that has a really nice abstract that nicely summarizes things. The results here are very nicely illustrated graphically and visually in figure 2, where The top 8 panels, so panels A through H here, are stick figure tracings of how the model moved when it could freely swing its arms here. Okay? On the bottom are how the model moved when it could not freely swing its arms, when the arms was locked in a slight shoulder position there with the elbow slightly behind the center of the trunk there. Notice the pose of the arm is kind of locked in that pose relative to the trunk the whole time that it's doing this restricted arm swing jump. While with free arm swing, the model can freely move its arms, and the arm is in a different pose, or at least the shoulder is in a different pose every frame here when it was doing the free arm swing jump. So what was different here? The x-axis here, it's not labeled, but you can see here, compare where the toe is at the start versus where the toe ends up. It's pretty much on the far side, pretty much made it all the way across the x-axis of the panel here, versus with the restricted arm swing, starts in the same spot, but then the toe ends up quite a bit before, quite a bit less distance traveled here when they did the restricted arm swing jump versus when they had the free arm swing jump. And this is how performance in the standing long jump is measured. You measure where the toe starts and then where the toe ends up when you land there. Okay? I should have clarified that this was a standing long jump. This was not like a track and field sprint down the runway and then jump type of long jump. This was a long jump that started from a static posture, from standing still. Okay? In the sports world, this is typically called not a standing long jump. You might sometimes hear this referred to as a standing broad jump, like in the NFL combine. This is a common test that the prospective NFL draftees will do. So stand still and jump as far as you can from a standstill, not from a running start. So notice here that the way the model chose to swing its arms when it was able to swing its arms and when it jumped further was when it was on the ground. So from frames A through C here, it started with the arms at its sides and then swung the arms forward and upward, okay, while it was on the ground here. Then it leaves the ground and the arms are airborne, or then it's airborne and the arms are still kind of swung upward there. And then while it's airborne and while it's getting ready to land, it then starts swinging the arms back, right? It starts moving them back down, and right before it lands, actually ends up with the arms back behind, a little bit behind the body here. Okay, which of course in the restricted arm swing jump, it wasn't doing any of those things because the shoulder was locked in that position. It couldn't move it like that. Okay. So why does swinging the arms forward like this? Why does that help me jump further in terms of why do I do that when I'm on the ground? And then why, when I'm airborne, why does swinging my arms back like that, why does that help me jump further? Why are these good things? Why this helps you on the ground, or why it might help you to swing the arms to jump further, to swing the arms forward and upward like this when you're on the ground, that's the more straightforward question. So let's take a look at that. And I will pull up my video here. I'll give you my, again, amateur biomechanics lab demonstration there. Got my Team Spirit Maryland shirt on today. Okay, so hopefully you guys can see my whole body here. Notice what happens, and I'll just do a simple example here. One of the things that we highlighted last time with arm swing in vertical jumping is that by raising the mass of my arms up, this raises the center of mass of my whole body up, so increases the potential energy of my center of mass, and this helps me jump higher because then I start from a higher or a greater height of my center of mass above the ground to begin with, right? So I'm kind of starting with an advantage with the center of mass already a little bit higher in the air than if I had started with my arms down like this. The other thing that's happening, and possibly the more important thing, is that as I'm raising my arms up like this, I'm not just at that time increasing the potential energy of the center of mass, I'm also increasing the kinetic energy of the center of mass. That mass is moving upward at a certain velocity, so I'm increasing not just potential energy, the height above the ground, but while I'm doing it, while I'm doing that motion, I'm increasing the kinetic energy, which is going to help me increase that takeoff velocity, which is a key factor in determining how high I jump. Okay? So similar thing is happening here when I am trying to jump as far as possible. Okay? Then it's not just my vertical velocity at takeoff that matters, it's also my horizontal velocity at takeoff that matters. So I want to get my velocity going in this direction at a certain angle away from the horizontal. I don't want to go strictly vertically. I don't want to go strictly horizontally. I want to go at some angle in between there that's going to carry me through the air a long horizontal distance. Now, why does arm swing help with that? You can demonstrate this for yourself simply. If you just stand straight up and down here, and then just swing your arms forward and upward as fast as you can. And don't do this like violently, like, don't muscle up and just do it absolutely as hard as you possibly can. Don't want anybody to hurt themselves. But do it under control, but do it as quickly as you can. And observe where this takes your body. Observe where it feels like you're moving. So I'll demonstrate here. I'll just stand here at the side, just kind of nice and relaxed. And I'm going to swing my arms upwards and forwards as fast as I can. Notice where that took me. It took me forward, and it's kind of hard to see, but when you do this yourself, you'll feel that it's lifting you up a little bit, because it's indeed lifting your center of mass upwards in your body, and also while you're doing it, increasing the kinetic energy upwards of the center of mass. And also, since I'm moving my mass forward, by swinging that arm mass forward, I'm also increasing my kinetic energy and my velocity in the horizontal direction. So you can go from zero velocity here, standing still, to a non-zero velocity by simply swinging your arms like that. So that right there, I think, makes a lot of sense from an energetics perspective in terms of why arm swing and specifically swinging the arms forward like that in the first few frames here on the ground helps you jump further with the arm swing action there. Okay, what's a little bit more mysterious is, and what's a little bit less clear, is why once you're airborne here in frame D, why swinging the arms back behind the model like this, why does that help? Why is that a beneficial thing for jumping further? It presumably is a beneficial thing because remember the goal here was jump as far as you can at all costs, and so the model presumably was gaining some benefit from doing this, otherwise it would have moved its arms in some other way. The argument that they put forward here is that if you notice, and it's not always super noticeable, but if you look at especially frame C with the free arm jump versus frame K, the third frame in both jumps. So comparing the third frame, the pose of the trunk at takeoff in both the arm swing in frame C and the restricted arm swing here in frame K, notice how much more forward inclined the trunk is there. Okay? And then it's also noticeable here if you compare the fourth frame, frame D in the arm swing jump versus the fourth frame, frame L in the restricted jump, the trunk is much more forward inclined, or the trunk is leaned much closer to the ground than in frame L here where the trunk is more upright. Okay? You can still see a little bit in frame E versus frame N. Here the trunk is a little bit more upright, and here it's leaned a little bit further forward in frame E. Then things kind of normalize a little bit for the last few frames as we get to the landing there. But that seems to me to be what the main difference here is in the airborne phase. I'm having my trunk in frames D and E inclined forward more, flexed forward more than I am without the arm swing in frames L and in frame M. So that's what they attribute the benefit to being able to swing my arms back like this, is that allowed me to, in the airborne phase, have a more forward inclined trunk. Okay? Now, why is that a good thing? Well, the trunk here is by far the largest and heaviest body segment, and it has the largest influence on where the center of mass is compared to any other body segment. So the more that you lean your trunk forward, the more forward the whole center of mass is going to go, and the further ahead your toes are going to go, and then at the end you put them in front there when you kick your toes out in the front there to land. Okay? So having your trunk leaned forward like this early on in this airborne phase, and in E more towards the middle of the airborne phase, compared to down here in the restricted arm swing having a more upright trunk, is just getting your whole center of mass a little bit further forward, even if your hip or whatever a specific part of the body is not necessarily tremendously further forward in those circumstances. The risk here in terms of why the trunk was more upright like this without the arm swing, that's part of what they refer to as a holding back strategy in throughout the paper here, where when I have my arm swing restricted, I'm not getting my trunk leaned as far forward as I can because I'm not able to rotate my arms backwards to kind of correct that motion later on when I need to land. Okay? If I got my trunk leaned forward too far here without arm swing, it may just be going progressively flatter and flatter and flatter, and I would not be able to get my toes out under me far enough to actually land successfully at the end of the jump. So they keep the trunk, or at least they think they keep the trunk more upright here, because if it leaned forward too far, you would get pitched far forward too much, and you wouldn't be able to get your legs under you and actually land. Okay? When I have the trunk inclined more forward like this, when I can swing my arms, this is because I can correct that position later on, right? As I get towards the end of the jump here, I can move my arms down and backwards to move my whole center of mass backwards a little bit, but then stick my toes out in front, because it's where my toes get, not where my center of mass gets. That's actually being counted here in terms of the distance that I jump. Okay? So long story short, arm swing on the ground, forward and upward to increase my takeoff velocity and my center of mass height when I'm taking off, and then arm swing down and eventually to the back as I'm airborne, so that I can pitch my trunk forward further, get my center of mass going forward further, but then correct that position at the end to still get my legs underneath me and land successfully. So arm swing, good thing for helping us jump high, and arm swing also a good thing for helping us jump far. So if somebody is seemingly doing good jumping technique, whether it's jumping for height or jumping for distance, and seems like they're not going as far as they should be able to, maybe it's not necessarily a leg thing, maybe it might be an arm thing. So maybe take a look at their arm swing or their arm strength, their arm power, arm action in general, and maybe there's an issue there. Maybe it's not necessarily the legs, maybe it's the arms, even though we tend to think of jumping as being a leg kind of thing. All right, that is it for now.